Here's the solution to S5, a classic area function problem. By that I mean they're going to give you the graph of some function, and then they're going to ask you questions not about this function that they've graphed, but about an area function that's made up of this graph. So this is the graph of f, okay? And they're going to be asking you questions about g, the function made up of the area function that is made up of f. So the first thing I do is realize with the fundamental theorem, I know the derivative of this area function. If you take the derivative of both sides of this equation, you get g prime equals f of x. That is, the derivative of an area function is this integrand with that variable put in. Now, sometimes if this is an expression, then you also have to multiply that by the derivative of that. That's really the chain rule. If this were some expression like x squared, then the derivative of this would be f of x squared times 2x. But as it is, since this is just x, the derivative of this integral, of this area function, is f of x. That means that g prime equals f of x. And I always have my students write, if you're given the graph of f and you're asked about g, well, this graph of f is also the graph of g prime. That's huge. That will help you throughout the whole problem. This is the graph of g prime. Okay, let's start with the problems. Part A, find g of 0 and g prime of 0. Well, g prime of 0 is really easy. Read it off the graph. G prime of 0 is 1. Okay, so we're halfway done with part A already. G of 0 is a little bit more difficult, but not terrible. We have to find the integral. We have to find the area under the curve, right? G of 0 would be the area under the curve from -3 to 0. We're just plugging 0 in for x. So how do I find the area from x equals -3 to x equals 0? Well, it's a trapezoid. I got to find that area in there. Pull out your area of a trapezoid formula and you'll get it. So you see there are two answers right here. Turns out the area of that trapezoid is 9/2. Okay, part B. Find all values of x in the open interval -5 to 4, so that's this whole thing, at which g attains a relative maximum. Justify your answer. As long as you realize you're looking at the graph of g prime, this is an easy problem. You got to remember that you can detect relative maximums by looking at where the first derivative changes from positive to negative. Relative maximums happen for a function f where its derivative changes from positive to negative. Well, we apply that to the function g here. We're looking at the graph of the derivative, so where does this graph change from positive to negative? Only one place, x equals 3. So we find it and we justify it by just repeating the thinking that we used to find it. So, whoops. Let's see what they say. Basically what we said right here. G prime, which equals f, changes from positive to negative only at x equals 3. All right, part C, find the absolute minimum of g. Okay, so that's different than a relative minimum. We need to find the absolute, which means we fall back on where can absolute minimums or maximums occur. Well, absolute minimums or maximums can only occur at critical numbers and at endpoints. So we have an endpoint at -5, we have an endpoint 4, and then we have two critical numbers. This one that we already talked about, but that's the location of a relative maximum, so it can't be the location of a relative minimum. And then we have this one. That's the location of a relative minimum, I can already tell, because the graph of g prime changes from negative to positive, so that's at least a relative minimum. It's a candidate for an absolute minimum. So we have to test two endpoints, these two, and we have to test this one critical number because it's a relative minimum. It could be the absolute minimum. So what do I mean by testing? We have to find the function values. We have to find g of -5, g of -4, and g of 4. These are all integrals that we have to find. They do that. This is interesting. G of 5 is the integral from -3 to 5. Let me clean this up a little bit. These areas, we have this area here and that area there, they cancel. But it's interesting to realize that because you're integrating that way, you're going from -3 to -5. This is actually the negative area, and that's the positive area. Never mind, they're congruent, they add to 0. That's why this first integral, or actually this first function value, is 0. This one, g of -4, we have to integrate from -3 to -4. That's just this one rectangle right here, not this one. Okay, that's a negative value. Use the area of a triangle, 1/2 base times height, you get -1. And finally, g of 4, that's the area all the way from -3 out to 4. Well, you can compute it, or you can argue that this really is a positive area. In fact, these two areas right here add to 0, and the rest of this area is positive. So I know that g of 4 is positive, guaranteed. Well, g of -5 is 0, g of -4 is -1, and g of 4 is positive, so -1 has to be the absolute minimum. Computing these three values and making some statement about the only place you can find absolute minimums are endpoints and critical numbers. That combined with these three computations is your justification. All right, finally, points of inflection. What's a point of inflection? It's the place where a function's second derivative changes sign. What do we have here? We have the graph of the first derivative. How can I get information about the second derivative when I have the first derivative, the graph of the first derivative? Well, the second derivative is given by this graph's slope. So I need to look for where does the slope of this graph that's presented change sign. That will tell me where g double prime changes sign. So where this is a positive slope, now it changes to a negative slope. There's a point of inflection. Be careful, that's a negative slope. This is also a negative slope, not a point of inflection yet at 0. What about here? The slope changes from negative to positive. So yes, that's a point of inflection. And also here, the slope changes from positive to negative. So 3 points of inflection, they want the x values, so it's -3, 0, and 2 as, -3, 1 and 2 as a list. There we go, that's a noisy S5.